with this I begin. So last time we proved using the fundamental theorem of the Morse theory, a classification theorem for manifolds, compact manifolds of dimension 2, compact surfaces. And the result, final result, it was formulated in several different ways, but one of the ways is actually the most convenient way, that every connected, compact, two-dimensional manifold is diffeomorphic too, and then a list follows. A sphere with handles and holes. So take a sphere, very round, make some holes and attach handles. Then a projective plane with holes again and handles. And the last, third possibility is to have a Klein bottle, again with holes and handles. A problem which remains is that to prove that actually within this, at least within these three series, no two manifolds are diffeomorphic to each other. Some part of this statement is very obvious and direct. If we have two such manifolds, which I have just listed, and if these two manifolds are diffeomorphic, then the number of holes for one of them is the same as the number of holes for the other one, because the number of holes can be described independently as the number of components of the boundary. Manifolds have boundaries. If manifolds are diffeomorphic, their boundaries are diffeomorphic. And a boundary is one-dimensional manifold, as we know separately. A one-dimensional manifold, compact one-dimensional manifold without boundary is a disjoint union of some amount of circles. And this amount certainly is a diffeomorphism invariant. That is, two one-dimensional manifolds, two unions of circles are diffeomorphic, then certainly the number of circles on both sides are the same. So the number of holes is invariant. Next thing, manifolds of dimension 2 is, the other dimension can be orientable or not. A sphere is orientable. Holes and handles will not affect orientability. So, and the projective planes, projective plane and Klein bottle are not orientable. So it is very much impossible that a sphere with handles is diffeomorphic to either projective plane with handles or Klein bottle with handles, because on one side we have an orientable manifold, and on the other side we have a non-orientable manifold. This is all which is clear immediately. Now, how to distinguish the remaining possibilities? There are many other possibilities. Say you have two spheres with handles, but the number of handles are different, not the same. Could they be diffeomorphic? Say the same for, or say you have a projective plane with 5 handles and Klein bottle with 7 handles, and the same amount of holes if you wish. Are they diffeomorphic? Actually, what is easier, to prove that two manifolds are diffeomorphic if they are diffeomorphic, or to prove that two manifolds are not diffeomorphic if they are not diffeomorphic? Usually, in topology and mathematics in general, it is easier to prove that, say, two manifolds are not diffeomorphic, because if they are diffeomorphic, then they are diffeomorphic, there is diffeomorphism. You try to construct a diffeomorphism, and you fail. What does it mean? Nothing. Maybe you should try in a different way or something. So in general, to prove that something doesn't exist may be easier than to prove that this something exists, because existence should be checked somehow, and non-existence may be proved with the help of invariance. Topology, especially algebraic topology, has many invariants, many ways to assign to a topological space or a manifold something. The something may be a number, maybe a group, maybe something very different. And say a number, because this is the possibility. And this number may be, and this might be a theorem, may be invariant with respect to diffeomorphism, homeomorphism, or even some more loose equivalence relations. So we have two manifolds for which we want to prove they're not diffeomorphic. And we just look at this invariance. If they're different, they're not diffeomorphic. If they're the same, well, take another invariant. There are not too many invariants in topology. However, topology, algebraic topology, is not our subject. So we should be cautious in using these arguments. So what? How to construct an invariant? There are different ways, and we have a choice. And one of the choices actually lies within our theory. We know that manifolds, for a compact manifold, there is a Morse function. We can consider closed manifolds without boundary, because if two surfaces are diffeomorphic, then they have the same amount of holes. We can fill these holes, and we will get manifolds without boundary, which remain diffeomorphic. So suppose that you have a manifold without boundary. Well, orientable or not, it's not important. And we consider a Morse function. Then this Morse function has critical points, finitely many critical points. Critical points have indices. And then we can do the following. Thank you. And then we can do the following. We can count the number of critical points of every index. So your manifold is M, it is n-dimensional, and suppose that it has, say, M sub k, a Morse function, M sub k of critical points of index k. Certainly, there are many Morse functions, and each has critical points and different amount of critical points. But it happens that the number sum of negative 1 to the power k mk, the alternating is 1. Alternating sum of these numbers does not depend on a Morse function. The same for all Morse functions. The proof is purely analytic, and actually some sketch of the proof is contained in my notes. But let's discuss how such a theorem can be proven. You have two Morse functions. You want to prove that these numbers are the same. it is always possible to consider a deformation of one function into another function. So a function varies continuously with respect to a parameter. So we have a family of functions, and we look what happens to critical points. Certainly, it is possible that for my function f, critical points are far from each other, and while they are far from each other, actually each critical point is moving, and nothing happens to it. Neither neither the number of critical points, nor their indices are affected. But at some moment, it is possible that critical points disappear or appear during this deformation. The best example is the following. We consider a function on a line. This function. It has a maximum, local minimum, right? Then we do this deformation. At some moment, a function is not a Morse function anymore because this critical point is degenerate. And after it, we have a very much smooth, very much Morse function. But this function had two critical points, a maximum minimum. That one has no critical points. So these 2 points kill each other, cancel. Actually, this possibility is the only possibility. Certainly, this is dimension 1. We can imagine that there are other dimensions, and the function actually, but still, with respect to some variable, with respect on some axis, the function is like this. This is precisely what happens. So here, 2 critical points cancel. What are their indices? 0 and 1. And it is possible to understand that actually if 2 critical points disappear simultaneously, it's only possibility for them. Then actually their indices, the difference between their indices is 1. So critical points of index 7 and 8 may disappear together, but not 7 and 9. If you do the same deformation in the opposite direction, you will see not the death, but rather the birth of 2 critical points. Again, of indices with the difference 1. And it is very clear that if we do this, then this number will not be affected. Because, say, if M7 and M8 both gain 1, then in this sum will stay the same. This is how it is proved. I will not do it in more details. Slightly more details you can find in my notes, also not a full proof. This number does not depend on the Morse function, and hence it is sort of a property of the manifold itself. This number is called, you know how, Virgil? How this number is called? You do know. It's called the Euler characteristic of the manifold. So the Euler characteristic of the manifold can be counted with the use of any Morse function. And this certainly gives us the possibility to compute it for not very complicated manifolds. If for 2 manifolds their Euler characteristic are different, then these 2 manifolds cannot be diffeomorphic. Homeomorphic are actually connected with some loser relations. Now, it is possible, I will show the result, but actually the computation is very elementary, to find Euler characteristic for all our canonical, for all our surfaces. So our surfaces are spheres, projective planes, and Klein bottles with handles, and without, I can say without holes, because the number of holes for two diffeomorphic manifolds should be the same, and we can fill up these holes, and the manifolds stay diffeomorphic. So we need to distinguish only spheres with handles, projective planes with handles, and Klein bottles with handles. And the fact is, I just mentioned this fact, and do not say anything else. The Euler characteristic of sphere with G handles projective plane with G handles, or Klein bottle with G handles. Is 2 minus 2g, 1 minus 2g, and minus 2g. This result, if you believe in it, actually settles all our problem, because we do not need to distinguish spheres with handles from projective planar Klein bottles with handles, because they are distinguished by the property of orientability. For spheres with different amount of handles, the Euler characteristics are different, 2 minus 2g, depends on g. For projective planes and Klein bottles with handles, Euler characteristics are all different, because if the Euler characteristic is odd, then this is a projective plane with handles. If it is even, it is a Klein bottle with handles. And then, if we know the Euler characteristic, we certainly can find G, the number of handles. This is all I wanted to say about this. Any questions, comments, whatever? And one more thing which I wanted to mention before I finish with the Morse theory. Suppose that we have some manifold of some dimension, some dimension, some dimension. And we want to construct, to find a good, a convenient Morse function. What is good or convenient? And the most naive, the most direct answer is we want that the number of critical points was as small as possible. We don't need many critical points, many critical values. Say, for a sphere, there is a Morse function with only 2 critical points. We know this by many reasons. For a torus, there is a Morse function which has 4 critical points, never less. Actually, I don't remember whether this problem is in my list of notes, list of problems, but usually I include this problem. If you want to construct a function, say in a torus, without the condition that all critical points are non-degenerate, let them be degenerate, then it's possible to find a Morse function, a smooth function with a number of critical points less than 4. Less than 4 is 3. And actually it is true, believe it or not, that for any two-dimensional compact manifold without boundary, connected surface without boundary, you can find a function with only 3 critical points. According to the usual theorems of calculus, we have 1 maximum, 1 minimum, definitely. So 1 more, which is should be very much degenerate as it is if it is not a sphere projective plane. Degenerate, yes. And there are constructions very much not belonging to the Morse theory, because who cares of such a function if you study Morse theory? But there are theorems within Morse theory, which also probably can be found in my problem list, but I don't want to prove them here. One is the following: if your manifold of any dimension absolutely is connected, well, without boundary, connected manifold without boundary, then you can always construct a Morse function with only one local and then global minimum and only one local and then global maximum. The number of global minima and global maxima should be reduced to 1 for every connected manifold. And this, it is actually a problem in my list of problems. You, Virgil, had a solution, I remember that. You don't remember. Oh, it's impossible to remember everything. Yes. This is one thing. So we can always do this. Another thing is the following. You see, if you have critical points of different indices, then directly you cannot say anything of their values, which is greater, which is smaller. But it's always possible to do something in this direction. Namely, it's always possible to have the following property, that if you have two critical points of different indices, then the one which corresponds to the smaller index has a smaller value. You understand? Your function has local minima, then critical points of index 1, 2, 3, 4, and so on. I can require that local minima are all less than all other critical values. This is very easy to achieve. Local maxima are the values, greater than all. There may be 17 local maxima, but all the values can be greater than the values in critical values which correspond to not to local maxima, to critical points of indices less than n. Moreover, if you have critical local minima is less than everything, then critical value of index 1, there will be greater than critical values, greater than the values at local minima, but we can require that they are smaller than the value at critical values at critical points of index 2 and more, and so on. So critical, when you take our very usual deformation of critical value from a value which is below the global minimum to the value which is above the local maxima, then what? You pass through critical values. First you pass through critical values of index 0. Then you pass through critical values of index 1, if any. Then 2, and so on. This probably can be achieved, and again, I am not proving that. There are other properties of the numbers of critical points, so-called Morse inequalities, which relate actually, the numbers critical point to other topological invariants. No, critical points are not numbers critical points, not topological invariants, so topological invariants. And there are also theorems which state that actually it's possible that all inequalities existing in this theory become equalities. A theorem belongs to Smale and actually has very strong topological consequences. I'm not discussing this. What I want to mention here, only one small thing, very small. Maybe you will not agree that it is small. Still will say this. Let us consider a three-dimensional manifold. And I assume that this manifold is connected and orientable, no boundary. So this is a closed three-dimensional manifold, connected and orientable. Suppose that we have a Morse function with properties which I have just listed. That is, it has only one local minimum, one local maximum, and the values at critical points are ordered accordingly the indices. Then look. So there is one minimum. So we consider our manifolds M less than or equal to C. And suppose that this C is greater than the value of the local minimum and less than the values other critical values. Then M less than or equal to C is above. Suppose then we go further and take C, which is greater than all critical values of index 1, but less than critical values of index 2. So when C grows, and we pass through critical values, we attach to this ball handles of index 1. A handle of index 1 is this. It is a handle which you use in the real life. Now, actually, when you attach a handle to a ball, it is possible to make it sort of inverted. That is, the orientations of these 2 points may be the same or different. I mean that when you attach this handle, you have a handle body which may be homeomorphic to a solid torus or homeomorphic to a Klein bottle. But if you require that your manifold is orientable, then this handle looks always like this. Not one handle. So you attach as many handles, the number of handles is the number of your critical point of index 1. The manifold which you obtain is called in topology handle body. It is actually a sphere with handles filled in a very obvious way. This is a three-dimensional domain. Domain in R3, you understand how it looks like. It is shown on this picture. So this manifold M less than or equal to C is a handle body whose boundary is a surface of some genus, a sphere with handles. Now, what can you say about the manifold where the value is greater than or equal to C? You see, it is the same if you replace your function f by the function minus f and c by minus c. You understand? So this is also actually a sphere with the same amount of handles, same amount, because these two manifolds have the same boundary. And we obtain the following Hegor's theorem, which was proved in the more than 100 years ago by a Norwegian mathematician, Hegor, which is actually shown on this picture. An arbitrary, connected, orientable, three-dimensional manifold is obtained from two identical handle bodies with the same amount of handles. by some diffeomorphism between their boundaries. You have two handle bodies, absolutely identical, and you can easily make them using the appropriate material out of plaster. And then so there is number G, number of handles. Also you fix some diffeomorphism. Between the two boundaries. And every three-dimensional manifold can be obtained in this way. Now my question to you, your impression. Can I say that, well, now we have a classification of all three-dimensional manifolds? Or something remains uncertain? What do you think, Virgil? Every three-dimensional manifold can be obtained from two identical sphere handle bodies by some diffeomorphism between their handles. What remains?
I think it's whole.
Hmm?
I think you already classified it whole, right?
That's done, right?
Yeah.
Maybe you will disagree with yourself. Yes, Doug.
Okay. I think we classified most of them between a few more conditions in there, like that it's compact and connected.
Yes. I impose all these conditions. Compact, is disconnected. Then the same can be said about every component. If it is not compact, well, this becomes certainly less clear. I agree. There are some classification theory for non-compact manifolds, three-dimensional, but we speak of compact case. Boundary actually will not do much. I prefer not to say much about the boundary without boundary. So too closed. I want to say something which it is even difficult for me to pronounce it. That this construction gives you a full classification of all closed, orientable, three-dimensional manifolds. Virgil buys it. I don't know how much he's going to pay for it. Duke says something not very clear. And Henry, do you know this?
I think you need a little bit more information about the diffeomorphism, because that's what's going to be complicated.
I see. There exists a very easy way to escape, which you want to use. You want to say, well, that we need a diffeomorphism. And this diffeomorphism, so we need to have a classification of diffeomorphisms of a sphere with handles onto itself. And this diffeomorphism, we don't know how to describe it, so we have, it is very easy to say, but for me it is very easy to reply. You're wrong, Henry. There exists a very clear and explicit classification of all diffeomorphisms. This was a classical result. I will not go into details, but actually diffeomorphisms, self-diffeomorphisms of a sphere with handles can be easily listed. There exists a very direct way of doing that. And actually, you could hear, this is Hegor splitting, also Hegor diagram. Hegor diagram is again, something very explicit which contains the description of diffeomorphism. No, I say that certainly it is not classification of three-dimensional manifolds, but by a very different reason. What remains unclear, we have two pairs of identical handle bodies with the same or different G, and two diffeomorphisms between their boundaries. We have two three-dimensional manifolds, and it is not clear whether these two will be diffeomorphic. Moreover, in mathematical logic, which we may respect, there is a theorem that there is no algorithm for distinguishing three-dimensional manifolds given actually by any way, in particular by Hegor splittings. So it is this classification certainly is excessive. We have all manifolds, yes, but we do not know which of them are the same. And this makes our classification very much incomplete. And this difficulty is not resolvable. At this moment, I finish with the more theory. I hope you agree this is a beautiful theory. And I want to use the remaining minutes, not too many unfortunately, to introduce our new last subject. This last subject consists in differential forms, integrals, Stokes' theorem, and the Ram cohomology. The first notion here is the notion number 1, is a differential form on a manifold. But there is a notion number 0, which belongs not to topology of manifolds, but rather to linear algebra. And here I want somehow to skip as much as possible, because it is not my subject. And it's much more elementary than my subject. But still, let us briefly discuss what we have here. So we have a finite dimensional vector space. For my purposes, over real numbers, but actually any field will work. If you are very strongly on the algebraic side, probably it is reasonable to say that any field of characteristic different from 0, from 2. But we consider real vector space of finite dimension. Then on this real vector space of finite dimension, there are linear forms. These are simply linear maps of this space into the ground field, into R. There are multilinear forms, bilinear form, three-linear form, and so on. Do you know what it is? Do you know what a linear form is? Linear form, you know what it is. Same as simply function on your vector space, which satisfies the condition that f of a plus b is f of a plus f of b, and f of lambda a is lambda f of a. It's a linear form. A multilinear form is a function of several variables. Every variable belongs to a vector space. For my purposes, the same vector space. And if you fix all the variables except one, then you will get a linear form. Right? For example, f of x comma y is xy, a function in the plane, R2. It is a bilinear form, because if you fix x or fix y, then what remains becomes a linear form. Right? Say f of xy is x plus y is not a bilinear form. Because if you fix x, say, let x be equal to 1. Then you get a function f of y is y plus 1, which is not a linear form. Okay? Okay. So there are multilinear forms. Next thing. A multilinear form depends on several variables. And then we may want to know how it reacts on the permutation of the variables. Two extreme cases. There are symmetric forms, which means that when you change the order of variables, the value remains the same. And there are skew-symmetric forms, which have the property that if you switch two variables, then the value acquires the minus sign. You need to write it. It is all. So there are symmetric forms and skew-symmetric forms. What I prefer to fix, is the number of variables. I say multilinear form, but let me say k linear forms. I don't want to say n linear form, because anyhow at some moment I will denote by n the dimension of the space. So some other letter. K linear form. I consider all k linear forms on a space of dimension n. This on some given vector space. These forms themselves form a vector space. If we take the sum of two multilinear forms, it will be again two k-linear forms. It will be again a k-linear form. If you multiply a k-linear form by a number, certainly it will be again a k-linear form. That's okay. So there exists a new vector space. The vector space, actually three more vector spaces. The vector space of all k-linear forms on our space, symmetric k-linear forms, and skew-symmetric k-linear forms. The dimension of our space is n. The dimension of the number of variables in the form is k. Do you know the dimensions of the spaces arising, if they are finite dimensional? First, all linear forms, all k-linear forms. What is the dimension of the space of all k-linear forms, my friends, on an n-dimensional space?
And choose K.
No, n choose k, we will have this answer to a different answer to a different question. Yes. No, this is simpler. If you want to know your k-linear form, it is sufficient. You choose some basis in your space, which has, with a kind permission, n elements and vectors. And then you apply your k-linear form to any combination of these vectors. You have a number for any combination. As a combination, you take I1 and so on, ik. Every I is between 1 and n. So you choose in any way k vectors from the basis. They may be the same, may be different, whatever. And you plug them into the form. You get a number. These numbers actually fully determine the form, and also they are arbitrary. By this reason, the number of numbers which characterizes a k-linear form is what? You know, a kindergarten problem. How many telephone number? So it's in some cities, some town, telephone numbers are 6-digit, and every digit is 0, 1, 2, and so on, 9. How many telephone number is possible in this town? The answer is 1 million, 10 to the power 6. 10 is because there are 10 digits, but if we have not 10 but rather n, then it will be n to the power k. So n to the power k is the dimension of this space. Now, Virgil, I want to do something right for you. What if we take skew-symmetric forms? It is a smaller space because additional condition. What is the dimension of this space? And you have an answer. N choose k, because again we should plug basis vectors into our form, but our form is skew-symmetric. So first we can take them in arbitrary order, say increasing order. And second, you should avoid repeating any vector, because if there are two ei's, you switch them. Nothing changes, and still it should acquire the sign minus. So it should be 0. So actually, you should take the vectors number I1, I2, and so on, ik, with I1 strictly less than I2, strictly less than I3, strictly less than ik. And the number of such combinations is n choose k. Well. The number of the dimension of the space of symmetric forms, I will never need it. although it is also well known. Do you know what is this? So it is the number of sequences I1, I2, I3, IK, such that the sequence all between 1 and n, and non-decreasing, but the repetitions are possible. This is also sort of choose. You know what it is? How many sequences with this property? How many? So suppose that you have numbers, again digits if you wish, and suppose that in that town which we considered before, all the telephone numbers have this property that actually the digits follow in a non-decreasing order. So 3, 3, 4, 6, 6, 7 is okay. But 3, 4, 3 is not okay. Then how many telephone numbers will we have? My friends, it is not my subject. It is a problem from very elementary combinatorics. The answer is n plus k minus 1, choose k. Forget about it if you don't like it, because I don't need it. What is important? We will consider mostly, I can say solely, but you can easily say this, but never follow your restriction. We consider mostly skew-symmetric forms. Then the dimension of the space of skew-symmetric forms of skew-symmetric k forms is n choose k, which shows first of all that if k is greater than n, then there are no skew-symmetric forms. The measure is 0. If k is equal to n, the measure is 1. N choose k. In this case, we actually can ask another question, sort of shorter. Forget about k. Let us consider absolutely all possible exterior forms. So direct sum of the spaces of exterior forms of 0, 1, 2, and so on, n variables. About the total dimension. You know, there is again a simple rule in combinatorics that if you take n choose 0 plus n choose 1 plus n choose 2, so on, plus n choose n, then you get what? Oh, you know, 2 to the power n. Yes. So actually, 2 to the power n is the dimension of, in some sense, you can say this, of absolutely all exterior forms. Well, here I have to stop. We will need some other information from linear algebra, but not too much. And then we will pass to manifolds and consider the corresponding objects on manifolds, precisely as we have tangent vectors on manifolds and vector fields. We have, what I say, linear algebra object and something in differential topology. This is next time. So again, I will write a message to all of you. In particular, when I say all of you, I mean also people who decided not to come today, maybe because of the rain, maybe because of some other reason. And next, is it next? Can I say next Friday? I mean, or should you say this Friday? This Friday. So the day after tomorrow. You will have 5 simple problems. Probably it will take 10 minutes to solve them. So the subjects are all our subjects. I will write a message with a list of subjects, but you know them. Everything which we had, including the Morse theory and not including anything else. So Morse theory is the last subject.